Hi everyone, I'm happy to introduce our latest work, CTM-AI, a blueprint for general AI inspired by a model of consciousness. First, let's talk about the overall overview of CTM-AI. CTM-AI is inspired by the Conscious Turing Machine, or CTM, which is a model of consciousness. Our goal is to adapt this theoretical model to tackle real-world problems using state-of-the-art AI technologies. Our problem setting is the following. When we are given any type of multimodal input together with a user query, for example, what day is today? CTM-AI organizes multiple processors into a cooperative system to solve complicated tasks. These tasks can be multimodal perception, multimodal reasoning, tool and API usage, and multi-turn agent capabilities. All of them work together in a coordinated way to solve the task. Now let's talk about the CTM-AI processors. Currently, CTM-AI includes multiple long-term memory processors with specialized functions and reasoning capabilities. For example, one processor can be a text-based language model that answers questions like, "Why is the sky blue?" Another processor can be a vision language model that answers questions such as, "How many birds are in the image?" Another processor can be an audio language model that tells us what people are saying based on an audio file. We can also include a language model augmented with tools to answer questions like, "What is the time now?" All of these can serve as basic components of CTM-AI, and each processor outputs structured chunks. Next, let's talk about the dynamics of CTM-AI. CTM-AI handles complicated multi-step tasks through iterative inference dynamics. Let's start with a simple example that includes three long-term memory processors: a text LTM, a visual LTM, and an audio LTM. Suppose the input includes multimodal observations and a user query. The multimodal observations can include an image, an audio clip, and a text utterance. For example, the utterance says, "You have no idea what you are talking about." The user query is the person being sarcastic? Step 1 of the CTM dynamics is that each processor is executed independently to collect chunks from the LTM processors. Each chunk includes three components. First is the gist, which is the processor's answer to the query based on its modality. Second is the weight, which indicates how confident, important, or relevant the processor believes its chunk is. Third is the curiosity, which is a question proposed by the processor to improve the overall understanding. For example, the text LTM may output a gist saying that the utterance sounds sarcastic. It assigns a certain weight, and it proposes a curiosity such as, "What is the tone of the voice?" At the same time, the audio LTM may output that the voice sounds angry, with its own weight and possibly another follow-up question. After all processors generate their chunks, we move to the next stage, which is competition among chunks. All chunks are collected and compete based on their weights. The winning chunk is selected through a global weight sampling mechanism. This winning chunk is then pushed into short-term memory. The short-term memory works as a broadcasting station. It consumes the winning chunk and may produce a provisional output. For example, it may output, "The person is not being sarcastic," as the current best answer. When we move to the next step, the system enters a backward and iterative phase through downtree broadcasting. The short-term memory broadcasts the winning gist and curiosity to all processors in the system. For example, if the winning chunk includes a curiosity like, "What is the tone of the voice?" that question is forwarded to all processors, including the audio LTM and visual LTM. If any processor can answer this curiosity, then a link is formed between the related processors. For example, if the audio LTM can answer the text LTM's question about tone, then they form a link. This link indicates that they recognize each other's usefulness and can collaborate. To keep CTM-AI simple, there is no explicit mechanism for breaking links. If a link is no longer useful, a processor can simply choose to ignore it. Next, we move to multimodal fusion between linked processors. Before the next round of chunk collection, linked processors communicate with each other. For example, the text processor may ask the audio processor for more information about tone. The audio processor may request more textual context. Through this communication, their internal states are updated. After this fusion, a new round of chunk collection begins, and the CTM-AI dynamics repeat. So, the overall loop of CTM-AI is chunk generation from long-term processors, competition based on weights, short-term memory broadcasting, link formation between processors, multimodal fusion, and then back to chunk generation again. This is the overall dynamics of CTM-AI. We are grateful to our friend Michael Xuan for his enormous personal support and encouragement. We thank UniDT for their supporting grant of our work. We also acknowledge NVIDIA's GPU support. Hi everyone, welcome to the interactive demo of CTM-AI, a new multi-agent prototype inspired by the conscious Turing machine. This demo lets you type a question, upload supporting data, choose which processors you want in the system, and then watch how CTM-AI evolves and reasons step by step. Let's start with a simple example. Here, I'll enter a query that requires recalling a person's name. The question is, who leads this research group? Where the group name appears in the image. As extra context, I also provide a short sentence saying the professor is an assistant professor at the MIT Media Lab and MIT EECS, and I upload an image that includes the logo of the Multisensory Intelligence Group. We use this small example because it clearly shows how CTM-AI combines text, images, and tools during inference. Next, let's set up the CTM-AI. In this system, a CTM is built from multiple specialized processors. You can select different long-term memory processors, or LTMs, and combine them into one unified CTM. For example, we can include a vision processor to understand images, a language processor to interpret text, a search processor connected to a web search engine, a coding processor for programming tasks, and an audio processor for audio inputs. We also support additional API-based processors, such as news and social media tools. Now I'll click Start. You can see the processors I selected are initialized and assembled into the CTM-AI. Each processor has a specific role, and each one is driven by an underlying language model or multimodal model. For example, in this demo, the vision processor and the search processor are both powered by Gemini 2.0 Flash. At the beginning, there are no links between processors and no long-term memories stored yet. On the right side, you can follow the overall CTM dynamics in real time. Gist inference, up-tree competition, down-tree broadcasting, and then link formation and fusion between processors. As the system runs, you can see how different processors compete, collaborate, and connect to produce the final answer. After we move to the next step, each processor generates its own chunk for the query. Each chunk includes 3 parts: a gist, a weight, and a question the processor wants to ask. For example, the vision processor isn't sure about the lab leader's name. It produces a gist with weight 0.64, and its question is, what is the name of the leader of this research group? Meanwhile, the search processor is also uncertain about the leader, but it assigns higher confidence to its chunk. It outputs a gist with weight 1.62 and asks, what is the name of the research group mentioned in the image? Once we collect the gists from all processors, the chunks are sampled in a tree structure based on their weights. The goal is to select a single winning chunk to be sent into short-term memory. In this example, the search processor wins because its weight is higher than the vision processors, so its chunk moves up the tree and becomes the final selection for short-term memory. At this point, we treat the winning chunk as the system's final answer for the query at this iteration. The winning chunk is stored in the short-term memory workspace as output. This workspace is a broadcasting system that can consume the winning chunk and make minimal modification as the better answer to the user query. That completes one full forward inference cycle. But if we want to iterate and improve, the system continues. The winning chunk is broadcast back to the other processors through the downtree process. During downtree broadcasting, the winning gist is written into the long-term memory of every processor except the one that originally produced it. After downtree broadcasting finishes, we update the processor connections through link formation. A link can be formed when one processor can answer another processor's question. In our example, the search processor is asking about the group name shown in the image, and the vision processor can extract that information. So the vision processor answers the search processor's question, and they form a link, meaning they've identified a useful collaboration pathway. Once links are formed, the processors enter the fusion stage. Here, linked processors exchange answers to each other's questions and use that information to enrich their long-term memories. It's called fusion because the new knowledge gets merged into each processor's internal context, strengthening what they can produce in future cycles. Now we start the next iteration. Because the processor's long-term memories have been updated through broadcasting, linking, and fusion, they generate stronger chunks the next time they run GIST inference. In this case, the vision processor still not know the professor's name directly, but it has provided the search processor with the research group name. With that, the search processor can search online for the group and find the leader. As a result, the search processor updates its GIST with the correct answer. Paul is the director of the research group. In this round of competition, the winning chunk now carries the correct information. After uptree competition selects it again, the system outputs the final answer, the correct name of the research group leader. We are grateful to our friend Michael Xuan for his enormous personal support and encouragement. We thank UniDT for their supporting grant of our work. We also acknowledge NVIDIA's GPU support.